One of the many interesting applications in fluid mechanics, aside from fluid flow and hydrostatic forces, is the use of similitude. In this particular case, what we're looking at is how do we simulate flow that in the real world, say for example, we go to a water system and we have a 2-inch diameter check valve and there's 30 cubic feet per second of flow going through that valve. How can we simulate that in a lab where we have, say, a 3-inch diameter check valve? And then what flow would we have to operate it so that the operating conditions are similar? As we learned in the lesson, it's not just about geometric scaling. Geometric scaling is when you literally say, okay, I'm going to take, for example, a car that normally is 25 feet long, and I'm going to bring it down to, say, a 1 to 100th scale so that I have a model that's 2.5 feet long. For us to really simulate the fluid flow characteristics, we have to look at things beyond the geometric similitude. In this case, we're going to look at dynamic similarity. Okay? Now remember, there's actually 3 types. There's geometric, dynamic, and kinematic. If we can get dynamic and geometric, we automatically will have the kinematic similitude as well. So let's go ahead and start with this problem. As I mentioned before, we have a scenario where in the real world it's a 2-foot diameter check valve. In the model, or what we're going to have in the lab, it's a 3-inch. And the question is, how do we simulate the flow from 30 CFS to a flow that would give us similar flow characteristics and behavior in a lab where we have a 3-inch diameter? So let's start by looking at the different types. Now, with dynamic similarity, you have to look at the various non-dimensional parameters that you can use, like Froude number, Reynolds. For this type of application, we have a pipe flow, essentially. It would be easiest just to go with the Reynolds. And what we're looking at is we're going to say the Reynolds number for the prototype, or the real life scenario, has to be equal to the Reynolds number for the model. And if we go back a couple lessons when we learned about Reynolds number, we know that it's the velocity. So we're going to use velocity of the prototype, in this case times the diameter of the prototype, over the kinematic viscosity of the prototype. And likewise, we have the same terms, but for the model, we have the velocity of the model, diameter of the check valve in the model, over the viscosity that we're going to be using in the model. Now, I didn't really state it here, but in this application, we're going to have water going through both scenarios, right? And we're going to assume that it's at the same temperature. So we're going to assume that the viscosity of the prototype viscosity, the dynamic viscosity, is equal to the dynamic viscosity of the water going through the model, which again is a realistic assumption because we're using water flow in both applications, assuming it's at room temperature. Okay, so that would eliminate these 2 terms here. Okay, we don't know velocity, but we know flow, so we can go back and use continuity. Recall with continuity that the flow is equal to the velocity times the area. Or if we rearrange this for velocity, the velocity can be expressed as the flow over the area. And so what we're going to do is we're going to take this and we're going to substitute this term in for here and here. Okay? So we have the flow going through the prototype times the diameter of the valve in the prototype. Okay, we're going to have to put the area term in there. So we'll have the pi over 4 diameter of the prototype squared. That has to equal, again, we have the similar expression for the velocity. We have the Q of the model. We have the diameter of the check valve with the model. And then we have the area term, pi over 4. And then we have the diameter of the model squared. Okay, so we can simplify this equation a little bit. Cancel out the pi over 4 terms, right? And this leaves us with QP over diameter of the prototype is equal to Q model over the diameter of the model. And what we're after is the flow going through the model, so we're going to rearrange it for this term here. So this gives us the flow going through the prototype times the diameter of the check valve for the model divided by the diameter of the check valve for the prototype is equal to the flow going through. I'm just going to go up here and work up here where I have for my substitutions. So for my flow going through the prototype, we've got 30 cubic feet per second. diameter of the model, we've got 3 inches. We have to just be careful with the units. 3 inches is 3/12 feet. Okay, because again, we have cubic feet here, so we have to make sure we have feet there. We'll divide all that by the diameter of the prototype, which is a 2-foot diameter. All right, and all that's equal to what we had on the right-hand term, the flow going through the model. When we do the final calculation, we get the 3.75 cubic feet per second is the required flow going through the model. Okay, so in order for this application to have complete similarity, okay, again, geometric and dynamic. On the dynamic similarity side, we use the Reynolds number approach, and we found that the flow conditions for a check valve, a 3-inch check valve operating at 3.75 cubic feet per second, is similar to the flow conditions experienced when you have a 2-foot diameter check valve operating at 30 cubic feet per second, which would be what you see, for example, in a water system versus what we have here in a lab. And with that, that concludes our example similitudes.